So the last time we talked about graphing quadratic equations, we looked at examples that were carefully chosen so that we could apply. The ideas about transformations that we already knew. To go from the base graph, right, y equals x squared, to the graph of whatever parabola we've been given. What if we have a situation like this, or a much more common situation, where we just have some random quadratic equation, and we want to graph the thing? Well, the easiest method, from what we know so far, is just brute force. It's pick some points. We know it's going to be U-shaped, right? And we know, because the leading coefficient here is 1, that's positive, we know it's going to open up. So let's see if we can get a couple points on the graph and see where that leads us. So first, I'm going to kind of do the obvious thing, I guess, and see if we can find the x-intercepts. Right, so to find those, I'm just going to set x squared minus 2x minus 3 equal to 0. And solve this equation. Well, I picked the numbers nicely, right? This one factors. That's x minus 3 times x plus 1. And if we set those two linear factors equal to 0 and solve them, we get our answer. The x-intercepts are at negative 1 and 3. So if I graph those, it looks something like this. Okay, so now the big question is that good enough? Does having those 2 points uniquely determine a parabola? Is there only one that goes through it? And unfortunately, the answer to that is no. For example, there's this one, but then there's also this one, and there's also this one here. Right? There's actually infinitely many parabolas that only go through those 2 points. Let's try this again. I've got our this is the same function, same 2 x-intercepts. Only now I found another point here, right? I found the y-intercept. Y-intercept is almost always a good point to go for if a function has one, because it's generally pretty easy to find. So now I've got a third point, right? I've got my 2 x-intercepts, I've got my y-intercept down here, and that is enough. And that is enough to uniquely determine a parabola. In this case, it's going to look like this thing. Okay, so that's one method. Right? Find these 3 specific points. Not always the easiest method. If you take this example here, that doesn't factor. Now we could still find the x-intercepts, absolutely. It's going to require the quadratic formula, so we're going to end up having to go to decimals in order to graph them. But even this isn't a guarantee, right? You in your algebra classes, you've seen plenty of quadratic equations that don't have real solutions, right? And there are parabolas that don't even have x-intercepts. Okay, so one approach to this is just to find the coordinates of any 3 points, right? In this case, I made a little table here, right? I just picked 3 random x numbers, negative 3, 0, and 1, found the y values that go with them, and that gives me 3 points. Negative 3, 7, 0, 1, and 1, negative 9. Now this time I know my parabola opens down because the leading coefficient is negative 2, right? That's less than 0. So if I draw the parabola through here, I get something like this. Now, this is not the ideal method for doing this. Right? How did I know it looked like that rather than, say, having the vertex off to the left of negative 3 somewhere? Right? Well, the answer to that is I was using a program to do this that kept me constrained to a true parabola shape. So if I had gone kind of off the rails like that, it wouldn't have worked. And even then, you can see it's not quite the perfect fit that we might have liked. So yes, finding 3 points works, but it works best if you have some kind of technology solution that's doing the ultimate result, right? So that you know you're getting the parabolic curve through the points. Okay, so what if we don't want to do that? Well, so a few minutes ago, I hinted at there being a method that only required 2 points instead of 3. So let's take a look at that. Let's say this is the same equation, but we're going to do it again using this new method. First thing I'm going to do is find the coordinates of the vertex. Right, remember a couple lectures back, we derived a formula for that. The x-coordinate is negative b divided by 2a. For our function here, b is negative 8, and a is negative 2. So if we put those into the formula, turns into negative 8 divided by 2 times negative 2. Right? That's a negative to keep track of. But you simplify that, it's just negative 2. Okay, so we need the y coordinate. Right? To get that, I'm going to go back to the function, put negative 2 in there for x. You get, again, lots of negatives floating around there. Negative 2 times negative 2 squared minus 8 times negative 2 plus 1. You simplify that, you get 9. So our vertex is at negative 2, 9. Excellent. There's 1 point. Still need a second one. The second one, again, I'm going to go to the low-hanging fruit. I'm going to find the y-intercept. If we put 0 into our formula for x, we get y is equal to 1. So 0, 1 is my y-intercept. And that's enough. There is only one parabola that goes through both of those points and has the upper point at the vertex. And that really is the magic part of this, right? If you know the vertex of the parabola, then all you need is one other point to get the graph. And it's going to look something like this. Now, let me make an interesting point about this, right? That second point, happened to be the y-intercept, is 2 units to the right of our vertex. If we go 2 units to the left, if we go over to negative 4, and I didn't work this out, but you can do it yourself quickly enough, easily enough. If you substitute negative 4 in there for x, you get 1 again, right? You get this point here, right? That's really an interesting symmetry, right? You notice that this graph is symmetric. If we fold it over, the line coming down through that vertex, the two sides are mirror images of each other. That's why if you know the location of the vertex and you know the location of a second point, you kind of automatically get the location of a third. Right? It's kind of a nice little confirmation that we were on the right track here. All right, so now we've got several different ways to graph a quadratic function. Most of the time, I'll use if I can look at it and immediately see that it factors, I'll go with the first method and just find the x-intercepts and the y-intercept. There's my 3 points. Okay. If it's not immediately obvious to me how it factors, so I can get those x-intercepts, then I'm going to go for method 3. I'm going to find the vertex and the y-intercept. That's enough to get me the graph. Okay, so kind of moving on from here, we're going to continue to make use of that vertex formula. We're going to take the next several lectures and look at what are called optimization problems. Right? In these situations, we're given a function. We're going to be just using our quadratic functions. And you want to find its extreme value. You want to find where it's at, either its maximum or its minimum. So first we're going to look at some kind of interesting theoretical results. Then we're going to use those along with this vertex formula to answer some kind of practical questions.